time, not too long ago. The place, a busy airport. The situation, a commercial jet taking off, a small aircraft waiting behind it, the pilot eager to be on his way. These were the ingredients of a problem that was to become a growing concern to the entire aviation community.
Tower, this is November 3044 Zulu, ready for takeoff.
November 3044 Zulu.
El Paso Tower, cleared for takeoff. Caution, wake turbulence from departing jet.
Caution, wake turbulence. In those days, pilots could heed that warning or not. It was up to them. For those that chose to ignore it, the results were sometimes unfortunate indeed. For years, wake turbulence has been a concern for pilots. It is a problem that can be encountered whenever you operate in the vicinity of other aircraft, particularly large ones. It can happen while taking off or landing. It can happen in level flight. It can happen whenever a plane hits the turbulence present in the wake of another aircraft. Have become even larger and heavier, the problem of wake turbulence has become more serious than ever. This has caused the FAA to establish minimum separations for other planes following heavy jets. How were these separations determined? For years, we have known that all aircraft produce wake turbulence. It is a phenomenon that involves several factors. Among them, prop wash and jet blast, both generated by aircraft engines and quickly diffused in flight. The more important factor in wake turbulence is caused by the flow of air currents around each wing. These currents are normally invisible, but we know they develop an unusual pattern at each wingtip. This smoke tunnel test shows how the currents form into a violent vortex behind each wing. Every aircraft has two wingtip vortices, like this, trailing out behind it. They may stretch out with significant strength on the order of 5 miles, and may persist at diminishing velocities long after the aircraft is passed. Wake turbulence at high altitudes does not present a problem for most general aviation pilots, but it can cause real trouble to light aircraft that encounter it at low altitudes, where there is little room to recover from an upset. For a number of years, the FAA has been carrying out a research program to learn more about wingtip vortices. It has long been known that the heavier the aircraft, the more severe the turbulence it generates. That's why the introduction of the first generation of jet transports drew special attention to the problem. As early as 1963, tests were conducted to determine the characteristics of wingtip vortices. Smoke grenades set up alongside runways at various airport locations permitted the vortices to be studied and measured. These early tests showed the development of an axial flow in some vortices, a sort of horizontal tornado. It was also learned that helicopters in forward flight create twin vortices very similar to those of fixed-wing aircraft. Over the years, the research program has continued, with the National Aeronautics and Space Administration playing a significant role. At the Marshall Space Flight Center in Alabama, laser beams are being used in an attempt to measure the tangential velocities of the vortices and determine the forces they exert. Much of the FAA research effort has been carried out by the National Aviation Facilities Experimental Center near Atlantic City. Flight tests past smoke towers show how the vortex from the left wing turns clockwise when viewed from behind. It takes a few seconds for the right wing vortex to reach the smoke tower, but when it does, its counterclockwise motion is evident. Clearly then, the two vortices turn inward toward the plane's flight path. This kind of testing has provided valuable comparative data about the sizes and forces of vortices and their horizontal gradients. In early 1970, the Nuclear Reactor Testing Station in Idaho, a facility of the Atomic Energy Commission, was chosen as the site for one part of a three-phase wake turbulence test program. An FAA research team was on hand to observe smoke tower flybys of the new generation of heavy jets compared to other aircraft. The FAA flyby tests were seeking to determine whether or not the new large heavy aircraft created wake turbulence that was significantly more severe than that created by the older transports. In Washington State, the second phase of the test program was being carried out by Boeing. These tests concentrated on the 747, first commercial heavy jet transport to become operational. Special smoke-inducing oil was injected into the normally clean-burning engines, so the vortices could be seen. The 747 was followed in a number of touch-and-go landing situations by a smaller transport aircraft, flown by FAA and company test pilots. These pilots observed that the wake turbulence from the heavy aircraft up ahead was more significant than that from other large planes, in that its field of influence is greater. The test program was carried out under a variety of weather conditions. Wingtip smoke generators used to visualize the vortices in earlier tests were later discarded in favor of the engine oil, but they did permit a careful study of the smoke patterns in touch-and-go landings. The wingtip vortices could be seen stopping as soon as the aircraft's nose wheel touched down on landing. It was not until the nose wheel lifted on takeoff that the vortices reappeared. This confirmed what had been discovered by earlier research. Wingtip vortices occur only when lift is created. At Edwards Air Force Base in California, NASA's Flight Research Center was the scene of the third phase of the 1970 flight test program. Here, at the birthplace of supersonic flight, were housed some of the most advanced flying machines in the world. Alongside them was a small general aviation aircraft, turned into a flying laboratory by the installation of special instruments to measure and record roll rates, control forces, and acceleration changes. Also on hand was a typical general aviation jet. Both these small aircraft were to be flown by senior FAA and NASA test pilots, as close as possible in the wake of a heavy military aircraft, the C-5A. It quickly became obvious that small planes should stay out of the area of significantly strong vortices from heavy aircraft. At 3.7 miles back, the test pilot intentionally placed his aircraft in the core of a vortex. This is the result, a full 360-degree roll. All this research told us quite a lot about the strength of wingtip vortices. We learned that they swirl inward, creating a strong downdraft between them. If a lighter plane encounters a vortex close behind a heavy jet, it can be flipped over on a wing, or even rolled all the way over. If the encountering plane crosses the wake, it may hit a severe updraft, downdraft, then another updraft in less than a second. When the generating aircraft is taking off or landing, the vortices descend into ground effect and then move outward at about 5 knots. However, a 5-knot crosswind will tend to hold one vortex on the runway, where it may be a hazard to other planes. The other will move at about 10 knots across a parallel runway, should there be one. This could present a hazard to planes landing there if it's within 2,500 feet. We learned that the new generation of heavy jets creates wingtip vortices that are severe, with relatively the same tangential velocities as those created by intercontinental transports already in service, but with a greater field of influence. We learned that as the wingtip vortices of all aircraft tested stretch out, they remain close together laterally. They descend at about 500 feet per minute and level off at about 800 or 900 feet below the flight path. In clear, smooth air, the turbulence may persist for some time. However, atmospheric instability hastens the breakup of the vortices. The turbulence also tends to become less severe when the flaps are lowered on the generating aircraft. We learned that turbulence gets worse as the speed of the generating aircraft decreases. In general, then, heavy, slow-moving aircraft pose the worst problem. Since more and more of these aircraft were going into service, something had to be done to enhance the safety in the terminal environment. The answer was controlled separation and pilot education. Research indicated that a 5-mile minimum separation should be maintained when within 1,000 feet below and behind any aircraft capable of gross takeoff weight of 300,000 pounds or more. This separation will vary depending on the size of the generating aircraft versus the encountering aircraft. This was translated into time intervals for landing and takeoff situations. These separation standards, put into effect in mid-1970, are applicable to all IFR traffic being radar vectored and to VFR departures. Pilots of VFR arriving aircraft are expected to maintain their own separations. This is why pilot education is so important. It's the chief way to minimize the possibility of an encounter with wake turbulence. Even when air traffic control separates you from heavy aircraft, it's wise to follow certain sound operating procedures when flying near them. You know that wingtip vortices cease as soon as an aircraft completes its landing. So you can expect the wake turbulence to be in this area, behind and below its flight path. Certainly then, if you're coming in behind a heavy jet, you should stay above its flight path and land beyond its touchdown point, even though the prescribed time interval has been applied. The same holds true on takeoff. You should lift off beyond the point where the landing jet touched down. Similarly, a departing aircraft does not begin to generate wingtip vortices until it becomes airborne. It is the area above his flight path that should be free from turbulence. Even though you will not be cleared to take off until the prescribed interval, you should still plan to become airborne before you reach the jet's liftoff point. Then you should climb quickly and turn upwind from its flight path as soon as possible. If you plan to take off across a runway that has just been used by a large aircraft, you should not expect air traffic control to clear you until the prescribed interval exists. Once aloft, if you find yourself flying behind a heavy jet at the same altitude, stay at least 5 miles back. Better yet, stay slightly above or more than 1,000 feet below it. Try to avoid landing and takeoff corridors used by heavy jets around busy terminals. You might want to consider using satellite fields where heavy aircraft don't operate. Be especially alert whenever you're operating at an airport with dual runways closer than 2,500 feet. It's possible for a vortex from an aircraft landing on an upwind runway to be blown right in your path. And this is what can happen. Turbulence from wingtip vortices continues to be a serious problem today. For this reason, the FAA, NASA, and industry research programs go on. They've already shown the need for the current minimum separation standards behind heavy jet aircraft. Now, as fast as new information is acquired, it's being carefully analyzed to see if further control action should be taken or additional recommendations made to the flying community. In the meantime, all pilots should stay as far as possible from heavy aircraft and continue to heed the warning, caution, wake turbulence.